In this video, I'm going to talk about small signal amplifier, and it's a common emitter amplifier CE configuration. How do you know it is CE configuration? My input, so if you look at this transistor, this is a NPN transistor. I mean, the arrow supposed to be that arrow supposed to tell you. I forgot to add the arrow. So it's an NPN transistor. Now my input is connected to the base. That's my base. Input signal is right here, and output is connected to the collector. So what will be the common terminal? Then emitter must be the common terminal. So that's the reason we call this as CE amplifier, common emitter configuration. So here we have coupling capacitors, the CB, CC and CE. Most of the cases these capacitors are very big numbers, so that way when it comes to the AC, when it comes to the DC, sorry, in DC circuit, they're going to act like open circuit. So frequency is 0, right? So XC is 1 over omega C. As frequency is 0, this value is infinite. So that acts like a infinite impedance in DC circuit. Now we're going to do the DC analysis. So in DC analysis, this part is going to be disconnected because the capacitor is going to disconnect it. This is going to be disconnected. Capacitor is going to disconnect it. Capacitor is going to disconnect it there to at collector. So in DC analysis, here to simplify this, I'm going to assume that this is working in active mode of operation. In active mode of operation, I'm going to assume there is a 0.7 volts drop across B and E. I'm going to write a KVL equation in this loop. Okay, that's loop 1. So 0 plus 100k IB, 100k IB, that's IB, plus 0.7 plus 8.3k IE minus 10 equal to 0. That's the loop equation. So we know that beta equal to IC over IB, alpha equal to IC over IE, alpha equal to beta over beta plus 1. You need to remember all these three formulas. After substituting these two in the place of IB and IE, end up with finding IC equal to 1 milliampere, IE equal to 1 milliampere too. This is our DC analysis. But another important thing, we want to make sure that the voltage VCE is greater than 0.3 volts. So here I found VC, which is 10 minus of VC. VC is right there. 10 minus of VC equal to 5k times IC. So I found VC equal to 5 volts. Similarly, VE equal to minus 1.7. VCE we ended up with 6.7 volts, so which is more than saturation voltage. So we're good. We can continue. Now calculate the GM. GM is transconductance, change in IC with respect to change in VC. Okay, IC over VT. This is the formula. For time being, remember this formula. So here we're going to use the pi model. When do we use the pi model? As long as if emitter is grounded while doing AC analysis. So in this circuit, in this given circuit, while doing AC analysis, this capacitor is going to act like this CE capacitor is going to act like a short circuit. Okay, since it's a short circuit, this 8.3 kilo ohms no longer, I mean, this is 0 ohms parallel with 8.3 kilo ohm, there won't be any effective. So your emitter is directly grounded. If that is the case, we can use the pi model. That's what we are doing. So while doing pi model, you need to use R pi, which is beta over GM, and we can find R naught, which is output resistance VA over IC. Okay, R naught is the output resistance of the transistor, not the whole circuit though. Okay, so here VA is called early voltage effect. So that early effect was named after James M. Early. Okay, it gives us the relation between the variation of width of the base emitter junction BJT due to variation of the applied base to collector voltage. So we know that in active mode of operation, so here is my NPN transistor. So this is collector, base and emitter. Sorry, I'm using my PDF document, so it's jumping a lot. So here this junction is forward biased, we don't need to worry. This junction is reverse biased. Okay, while amplifying based on the voltage, what happens, the thickness of this is going to change. So that means the base width of the base is going to change because the depletion region is changing. Okay, what is the change? You can find out by using the early effect. Okay, usually that value most probably is going to be around 100 volts. Sometimes it can be like infinite. Okay, now we're going to do the AC analysis. While doing AC analysis, replace all DC sources with their internal resistance. Okay, so and keep the AC sources. So this is what the circuit is going to look like. Now I'm going to replace this transistor with equivalent circuit. That equivalent circuit is pi equivalent circuit. So here it is, the pi equivalent circuit. So we have R pi here, and R pi value we already found that above here. Where is it? Beta over GM 2.5 kilo ohms. Okay, now we have R pi and GM times VB. VB is the voltage right there across that R pi, and emitter is grounded. Okay, now we found R naught, output resistance is always between collector and emitter. As long as either one of them is grounded or both of them are grounded, then only we'll use the R naught. That makes it simple. I mean, R naught is anyway a very big number compared to the RC and RL. Okay, our goal is finding AV. AV is the voltage gain. So first we need to find V naught. V naught is right here, voltage across the output. V naught equal to, can I say these three are in parallel? R naught parallel with RC parallel with RL, load resistance. So, and GM times VB is a current. So why it is minus? It is minus always because the current is going away from the output. So the current must be coming from these resistors. So if that is the case, the bottom terminal is positive, top terminal is negative. So V naught must be negative. Okay. Now VBE equal to Vn. Input terminal is right here. So when we look at the terminal, from the input terminal, the voltage at this point is same as voltage at this point. Okay. Now based on that, I found AV equal to, if I substitute that, minus 97.6. So remember one important thing, in CE configuration, always gain is negative. What does it indicate? Basically, if I give the input sinusoidal waveform, my output sinusoidal waveform is going to be inverted 180 degrees. Okay, so that's what that negative indicates. Now gain at no load, V naught over V input. At no load, all you need to do is remove the load RL, so the rest of it you can find it. It's around negative 190.5. Input resistance. Input resistance is looking the circuit from the input terminals. Okay, so here I have to look from here without the source, so I can clearly see this and these two are in parallel. So that's how I end up with input resistance. Output resistance, same, we need to look from the output terminals. So when we look from the output terminals, here is a dependent source, right? I don't know why I opened it. So GM times VBE. Since I have a dependent source, I have to connect either 1 ampere or 1 volt to find out the output resistance. Okay, when you find that, it's going to be R naught parallel with RC. So the total output resistance is 4.76 kilo ohm. Okay, now overall gain is always AV, gain times input resistance over input plus R signal. So here is my R signal, here is my input source Vn. So basically overall gain, in that case we're considering the source resistance to what is the signal resistance. So we're going to use the voltage division rule. How much voltage we are losing at our signal, and the remaining is going to be Vn. That's what we're finding. So overall gain GV is nothing but output over V signal input. Okay, so I can write it as V0 over Vn and Vn over Vsig, and so you will end up with V0 over V signal. That's the overall gain. So now Vn, I can write it as like this. So that's how I ended up with AV is nothing but V0 over Vn. That's AV, and Vn you can use this formula. Okay, based on that I found overall gain is minus 90.2 volt per volt. Okay, I will stop this here. I think this is a different example. I'll stop this here. In the next video I'm going to solve an example with the T model. Thank you.